Hello everyone. So in the previous lecture, we have learned that classically we can think of light as electromagnetic waves. So now we are going to have a review of what waves are. So let's get started. So what is a wave? If we give a very vague definition of a wave is anything that moves. So for instance, we have a function fx, and the plot of this function is like this one. Okay, so now if we change the argument of this function from x to x minus a, where a is a positive number, what should happen then? So let us have some trial here. So for instance, we change the argument of fx with x minus 1. So what happens then? If we just change the argument from x to x minus 1, the function, which is this one, fx, just shifts a little towards this direction, and the amount of shift is just 1 in this axis. So if we just replace this 1 with 2, what happens? Well, the function fx shifts towards this rightward direction by the amount 2. So the thing that happens when we change this argument is that it shifts the position of the function here. So now if we change this a with something like v into t, where v is a positive number and t is time, then with the increase of time, this value of a will change, and this plot of fx minus a will start to move in the rightward direction. And this is what we can call a rightward propagating wave or forward propagating wave, this fx minus vt thing. Similarly, fx plus vt represents a leftward or backward propagating wave, where v is the velocity of this wave. Well, the wave we were previously talking about was mainly traveling waves. Now there is another kind of wave which is known as the stationary wave, and we will talk about it sometimes later. So let us repeat the previous work for a well-defined function like the cosine of x. Now, we all know how cosine of x looks like, right? It is something like this. And if we change the argument of this cosine of x, it would look like something like this. And what is the difference? You see that here the curve just shifted by this amount, pi by 4. And if we just change the argument x with x minus pi by 2, then that same curve will shift here by the amount pi by 2, like this. Now let's see, how does the wave cosine of x minus vt look like at different times t, where the velocity v is pi by 4 meters per second. So for that, let us start with t equals 0. Now for t equals 0, can you tell what should the graph look like? Well, where t is equals 0, so it would be cosine of x. So we all know what cosine of x looks like, right? Let's draw a cosine curve. The graph would look something like this one, maybe. Okay, so where along the x-axis we have time t, right? So here the axis is like, this is pi, so this is pi by 2, and this is what we call pi by 4. Okay, now after 1 second, what should the function look like? So let me copy this thing here, and paste it like this. And after 1 second, what should happen is this curve will just move a little towards the right, like this. Okay, so as you can see, the tip was here. Now the tip will be at this point where the distance is pi by 4, like this. Okay, and what happens for t equal 2 seconds? Well, we can draw that one too. So let me copy this thing again and place it somewhere here, like this. And what should happen is that this graph should move towards the right, and the tip of this function here is now at distance pi by 2. So this is how this wave is moving towards this rightward direction. Now you can have a visual representation of this thing by using a very good graphing app known as Desmos. So let's write down the equation of our wave here. Y equal cosine of x minus vt, where v was pi by 4. And if we set a range for the time from 0 to 100 seconds and start an animation, let's see what happens. So let's start, and as you can see, the wave starts to move towards the right as we increase the value of time. Now what happens if we just replace this minus sign with a plus sign? Then we see that the wave starts to move backwards. So we call it a backward propagating wave. Now, in both the cases, whether it is a forward propagating wave or a backward propagating wave, the shape of this wave remains the same. For instance, for this forward propagating wave, you see that with the increase of time, the shape shifts towards the right, but it is of the same shape. So we can say that the local disturbance does not get distorted. It keeps its shape. So if we describe a forward propagating wave by this equation, then the function g determines the shape of the wave. And this g could be anything. For instance, a sine, a cosine, or an exponential function, and so on. And this v determines the velocity at which the wave is propagating. We can describe a traveling wave by using a wave function psi, where this psi is a function of space and time. So we can write down psi xt as g of x minus vt. Now, an alternative way of writing down a traveling wave is this one. Now, can you tell me what is the velocity of this traveling wave? Well, for that, you have to take this k common, and the term that is with the t, this omega by k, is the velocity of this traveling wave. Now, there are mainly two types of waves: longitudinal waves and transverse waves. Now, in the longitudinal wave, the variation of waves are parallel to the direction of propagation of the wave. And for transverse wave, these variations are transverse to the direction of the propagation of the wave. For both these examples, the wave is propagating in this direction. But for the first example, the disturbance is parallel to this direction. And for the second example, the disturbance is perpendicular to this direction. So the first one we call this longitudinal polarization, and the second one we call this transverse polarization. So in space we have 3 dimensions, and for a direction of propagation there are 2 transverse directions to this. So there are 2 transverse waves in addition to the potential longitudinal one. Okay? And the direction of waves variation is known as polarization.